Hi, my name is Ryan, and I'm a student at Northwestern University. In this talk, I'd like to share with you a way to imbue context-aware applications with a richer understanding of human situations. Context-aware apps have the potential to shape how we think about our everyday situations and the activities we can do in them. For example, these applications might help us find opportunities for shared experiences across similar situations to connect with our friends. It's becoming easier to create simple context-aware applications due to better sensors and algorithms for detecting context. For example, mobile phones can sense a user's location and use a place API to know that a user is located at a restaurant serving coffee and tea. However, one thing to consider is how we can get these apps to trigger in situations where there's an opportunity to have a human experience. For grabbing food on a cold day, how would we express such a situation? This is not a situation that's typically captured by the context detectors. There's really no cold day food detector. So the challenge essentially is that we have ideas of human situations, but they are quite far from the machine's available context features, and we need a way to connect them. This paper is a step towards enabling that middle expression layer through providing designers the cognitive supports to do this bridging. For example, a designer can think of warm liquids or broths or spicy foods that get their spicy sweat on, and these could be links to detectable place features like ramen or Indian. And so this paper makes the following contributions. Through pilot testing, we discovered 3 bridging challenges when translating human concepts into machine features. We then developed Affinder, a programming environment that provides cognitive supports to overcome the bridging challenges. In a lab study, we show how Affinder's core features can support expressing human concepts using machines' available features. So let me jump ahead and show you how Affinder works. Affinder is a visual programming environment for defining logical expressions made of context features, which we call concept expressions. And designers can flesh out intermediate concepts like spicy food, and then these are further connected to context features like Thai or Indian. And overall, this workspace is a place for linking between human-defined concepts and the machine-detectable building blocks. But what we found in early testing is there's challenges in constructing these well. First, designers might find one context feature, such as a baseball field for the concept grassy field, but miss others that also match. And so to address this, Affinder uses Yelp reviews to create an unlimited vocabulary of terms associated with the context features, so users can discover relevant context. Second, designers can overfixate on their initial ideas for a situation. For example, the first idea that comes to mind might be a park for places to toss a frisbee. However, this could accidentally narrow the scope of their thinking, and they may not consider others. To address this, Affinder provides prompts to reflect on why an idea is appropriate for an experience, to then help users expand to more concepts or ideas. And third, designers may use a context feature that does not operate as they intended, such as a garden that is recognized as a park but does not qualify as an open area to play. To address this, Affinder provides tools to simulate on real-world cases and repair the expression to more precisely evaluate their concept. Let me show you a demo of Affinder. So a person has searched fields and found relevant context features like parks, disc golf, and football. They use the reflect and expand prompts to question why parks was an appropriate place for this experience. They realize that open grassy areas to play is the more general concept they belong to. However, open areas also might include open sandy areas, and this spurs an additional search for sandy places like beaches and lakes. Okay, so after composing those, we skip ahead to them simulating this concept expression. They find this case where a park that is also a garden is being classified as an open area to play. But gardens are too formal, so they exclude that and make the concept expression more precise. So now I'll share a few key results from our lab study, where we conducted a between subjects test with 14 university design students, comparing their usage with the full version with all its core features versus a baseline version? Well, we measure the breadth of place context features that were included in each construction. And the median constructions had more context features when designers had the supports for finding relevant context features and for preventing overfixation on their early concepts. People said that the cognitive supports, such as unlimited vocabulary search, helped with stretching their concepts of the situation they were trying to express. In this first quote, one said that seeing context features that were related to their initial idea but in a different way helped them generate more concepts they wanted to search. In contrast, in the baseline version, people tended to run out of ideas since their simple text searches were largely unsuccessful. Finally, simulation and repair tools help designers see the accuracy of their construction on real-world cases. This designer found campgrounds and baseball fields as open grassy areas for tossing a frisbee. While there were some cases that matched their prior notions, such as on the left where a campground had lots of grass and foliage, some cases revealed misconceptions, like on the right, where campgrounds, which can be mainly supporting water sports or like kayaking and rafting, actually do not represent that grassy area to play. And so now I'll describe our core takeaways. Affinder's cognitive supports were key to enabling designers to bridge the gap between human concepts and machine representations. Given this, we expect that others who research cognitive supports for areas like design ideation would be well suited for tackling such bridging problems. However, bridging problems are distinct from design ideation. In addition to helping designers stretch their concepts, designers are also finding implementable forms, in this case as machine representations, for their ideas. Second, there are many more context-aware use cases where a richer understanding of human situations, will be important. For example, digital workspace assistants could recognize when a person might be struggling to ask for help, and in a virtual reality use case, technologies might help users explore a variety of virtual environments that supports a personal activity. To imbue machines with this richer understanding, better detectors of context powered by technologies like computer vision will of course be a component, but context features may not directly capture what we care about as application designers, and thus we want to introduce bridging tools as a research area of focus for providing a language for communicating the human situations we want to detect that are not fully captured by the current machine features.